It's my name on YouTube. So talking about the limits, so we are starting calculus. And the first thing we are going to say here is that calculus is a study of change. So calculus is a study of change. If you look at any evolving system, we can measure it and model it and explain it through calculus. So if ice is melting, it's losing volume, it's losing mass, and we can capture that through calculus. If you are talking about going from point A to point B, you are driving at, I don't know, 10 miles per hour. You are changing position from point A to point B. We call that velocity. And again, it's explained through derivative, which is calculus. Accumulations are integrals and so on, accumulation of energy. So technically, any type of evolving and changing system is going to be understood and explained through calculus, which is the reason why calculus is the central study of every kind of science, of every kind, anything that is based off of mathematics is actually based off of calculus, before anything else. In limits, we are going to write as a notation, by the way, this book has the limit definition, the rigorous one, in 2.7, which is the last thing we cover. So we'll just go right into what the notation is. Limit x approaches a of a function f of x could be finite number, could be one of the infinities, could be does not exist. So these are the possibilities that you can find. So now, how is this basic notion of limit captured in this, the basic notion of calculus, which is motion, which is progression or a change? How's that in here? Well, you see that x approaches a. That's where the motion is. X approaching a. So within limit, that change that it's happening, the motion that it's happening is actually in that arrow where x goes to a. Now we're going to explore and see those kind of concepts when we do derivatives, when we do integrals later on. Now we're focusing on the limit. The next thing that we are going to understand here is that the limit, in its most basic idea, the limit is just a fancy way to compute y values in a function. So that's the most basic way you can think of a limit, because if you have f of x is equal to x squared, and you go f of 3 is 9, you used precalculus to compute that. The calculus version of it is limit as x goes to 3 of x squared is 9. You see that you got the same thing. Now we are going to discuss why is the limit so much more powerful than just the basic f of x equals x squared. How they're different. What other features it offers on top of just being able to compute function values. But in a nutshell, the limits just compute y values of functions. But it's a very powerful way to compute those values. So now let's just quickly look at the graphs for these. And this is where we actually get to understand how they're different. So if this is 3, then this is the point where it touches and bounces off, and this is where the 9 is, making sure that this point is 3, 9. So you shoot up from 3, it bounces off of the point on the graph, and it gives you what the y value, which is the answer, is, and precalculus is done. Now, if you had an open circle as this is coming in, the answer in pre-calculus would be does not exist. Right? Because there is no y value associated to this point. It's empty circle there, right? Calculus and limits will actually be able to compute that value. Now let's see why and how. So we're talking about the same function x squared, but now we're going to look at it through the eyes of the limit, which is the first calculus concept that we are learning. So here is the same graph, which is the x squared graph, and we're going to have our number 3, which is going to produce number 9. Now, how does the limit do this? Remember the word approach. That is the key. If you understand that as a word, you should be fine. I'm going to use the red arrow, and I'm going to literally walk on x-axis towards 3. That motion, me walking on the x-axis towards 3, is understood as approaching 3. I can approach the desk, approach you, approach the door. So approaching is meaning walking towards it. So we are taking all of these x values before 3 and one by one computing as we are approaching 3. We are going to 3, all right? Now that type of motion, you approaching 3, on the function translates into you walking up this line towards the point, which further translates into you approaching 9. So hopefully if I pick any point here, you see this, pick this one, it goes up, it bounces off. So, and then pick the next one, it gets closer. You see how it goes? Does it make sense? So we are picking random points, but closer and closer to 3, and we follow the trend that the answers will constantly be approaching eventually 9. Then we take the blue approach. I like to call this Romeo and Juliet approach, it's red and blue, right? So we approach 3 from the other side, which will go down the line, which will go down the y-axis again at 9. And look what happens. They meet at 9. Why is this? It sounds like much more work because you're computing a lot of points, right? Instead of just saying x cubed, x squared is 9, you're done, right? Well, 3 cubed. 3 squared, 3 squared is 9, you're done. But what happens if that point is not there? What then? The difference between your pre-calculus notion of figuring out y values and calculus notion of figuring out y values is that over here you're computing one point, and if that point is not there, you're technically done. You're screwed. That's it. Does not exist, can't do anything about it. In calculus, you will compute all of the points around it, except that point. And all of these will lead you into what the answer should be, which is the reason why it's powerful. Now, to bring this a little bit closer to you, we don't say we use calculus to fix a bridge, but if there is a break in a bridge, so here is one cliff, here's another cliff, there is over here water and stuff, and you have a bridge, but that bridge is broken right there. The way to fix this is not to go with the pre-calculus and go like done. You actually have to approach from this side, you have to approach from that side, you approach the problem point which is not there. Pre-calculus can't fix that, but you can't just teleport there, and if you do teleport there, just fall through, and it's dead. Alright? It is the calculus approach. You approach from one side, you approach from the other side, you work, you patch it all, and then people can drive over the bridge again. So that is the difference between computing the point directly versus computing infinitely many points to the left and to the right, and the answers to those lead you into what the answer for this should be. Now clearly, if you are computing something as x squared, this is the way to do it. But then when it comes to a very serious lab work, research work, engineering work, the other one is the one. I gave you the really loose example of a bridge, but I'll give you another example now for let's say, in electrical engineering. Does anyone know Ohm's law? Yes. What is it?
No.
What is it?
It's something resistors.
Yes. Good. So in Ohm's law, we know that the current is voltage divided by resistance. And in your outlet, you have 110 volts. And when you plug in the charger for your cell phone is maybe 110 ohms. And if it's 110 ohms, you get 1 amp on this side. Now you take a look at your charger, you kind of fine print and it says it's 1 amp. Well, plugging in 110 volts at 1 amp is 110 ohms. Now what happens if you short circuit? You take a piece of isolated wire and you just stick it into two terminals. What happens? Explosion. Why does explosion happen? Calculus. Now let's see how the calculus plays the role. So in the very short period of time, and listen to my words, resistance is approaching zero, which makes current approach what? Infinity. You see that? So if you short something, this is approaching zero, which makes this approach infinity. Now, if you study physics, you will see that current is proportional to temperature. If this one is trying to be infinity, this one is trying to be infinity. Explosion in mathematics is very simply explained as infinite buildup of energy over a very short period of time. Welcome limits. So, in order for you guys to catch these concepts when you start taking engineering physics to build things, if you don't get these kind of concepts, well, how are you going to build anything? If you don't understand how you make something explode, how are you going to build anything right? Sony builds awesome batteries that explode, right? Apparently, their engineers don't know limits, all right? Now, they went live. You see Sony suing me tomorrow. It's like, yeah. Well, no, their laptop batteries did explode at some point. So the idea here is to understand that we have this notion of approach. And if you look at this function, that's constant. That's 110 at all times. This is the variable which can be adjusted. It's either 110 or it's 0 or it's 17. The graph for this thing is this. Now, you can see, using your eyes, that as you are approaching 0 on our input R scale, which is your X scale, so technically this is your 1 over X graph. In this case, 110 over X graph. So as R is approaching this, your output variable, which is Y, which is I, is doing what? So this is the connection, guys, between your calculus, your limit, your graph, and all of the ideas that you actually need to be able to build anything across the board, whether it's mechanical engineering, civil engineering, electrical engineering, or you are in biology or chemistry, physics. It doesn't matter where you are. This is how you transfer these concepts into actual work. And if you never did an experiment, right, I guess you will be resetting some switches at home. So the current goes to 0, and you literally write it as the limit of 110 over R as R goes to 0, because the resistance goes to 0, the whole thing, you look at a graph, is trying to go to infinity. Now we'll cover this again in our section 2.4 next Saturday. This is just a little bridge, so I'm not putting this in notes because I will go over this in detail again next Saturday. Yes? This is called air conditioning. It's very loud. Yes, that's also next Saturday. But true, yes, the limit doesn't exist because this limit and this limit are not the same. Cool. That's negative infinity, that's positive infinity. Awesome. So I hope that I was able to tell you what the limit actually is. It's a fancy way to compute y values. And now that you know how to do it, you can actually put that in a chart. So if I need to approach 3, I'm going to create a chart and pick 3 or 4 values before 3, 3 and 4 values after 3, compute their y values, and look at the trend. We are literally talking about middle school kind of level of work here, because you are picking 4 numbers that are smaller than 3 and 4 numbers that are bigger than 3, and computing their y values, right? So we talk middle school now. But I hope you understood the calculus part. The calculus part is the motion, the approach idea, and the idea that they both have to squeeze into the same point in order for that point to be the answer. And another notion is that that point doesn't actually have to exist, because you never use that point to compute. You use all of the infinity of the points around it to compute, but not that one. So that is the calculus version of computing y values, opposite to the precalculus, the one that you know when you stick 3 there and you say 3 squared is 9. So we cool with calculus? Let's do some middle school work now. So what we're going to do is we are going to pick, so this is 3, and this is what we don't know. We're going to pick 3 values before and 3 values after 3. Now let's pick some numbers that are close. Like 2.9 is close, and then 2.99 is closer, and then 2.999 is closer still. So you have like $2.90, $2.99, and then you go to the gas station, you have $2.99 and 9/10 of a cent, right? So that's that. On the other side, you might have 3.1, so $3.10 away, $3.01 away, and on a gas station, $3.01 of a cent there. You take the calculator and square each one of these numbers. You will see how this side is going to grow into 9 and this side is going to fall into 9. So take your calculators out and compute these values. You can use your cell phones. You don't even have to drag your cell phones are going to make nicer graphs than those TI-80 whatevers you have from last millennia. It's okay to use cell phones. And if you flip the cell phone sideways, it opens up more functions. Even iPhones do that. So it's apparently well understood by their team. 2.9 squared is how much? 8.41. 8.94. And then 8.99. I hope you guys see, and this is the red arrow. You see how it goes into 9? Right? You have $8.41, $8.94, $8.99. This is also where you understand that $8.99 is actually $9, not $8. I know you're all good with rounding, but you might want to help some other people with rounding. How about the numbers afterwards? So what's 3.1? 9.00, so 3.1 squared, 9.61. 301 is 9.06, and then 3.001 squared, 9.006, right? So it keeps introducing these zeros inside. And you see how this side falls into 9. So now you have the graphical representation and you have the chart as well. And here on the graph, you see that if I pick 2.9, 2.99, 2.999, the values that I'm getting here are the values that are here closer and closer to 9 at all times. And then the other one goes down. So these are the first two ways in which you learn how to take limits. You take limits by looking at the graph if you know how graph looks like. That's method number one. Method number two to take the limit is to actually make the chart, compute a whole bunch of points, and then compute that. And then method number three is going to be doing algebra. Now that's 2.3 actually. So what are we doing today is we are understanding the difference between pre-calculus and calculus portion. We are understanding the calculus part in terms of the approach. We are understanding the red side and the blue side. We have to understand that the red side and the blue side have to run into the same point in order for that point to be the answer. And I'm going to do more examples, but before I do that, I have to tell you one thing. Math and spoken English are usually perfectly aligned, except in this case. Most people see the limit, right? When you say the word limit, they think that's some kind of a maximum performance or something like that. You would say, I am pushing myself to the limit, I'm giving it all I have, and so on, right? Well, unfortunately, over there. Limits have nothing to do with max-min values. Nothing to do with extreme values. Limit is a simply answer to whatever input you give is going to give you output. Does this 9 look like it's either a minimum or a maximum of x squared? Hell no, right? So when you are thinking about this and you wonder next time whether the limit is some kind of maximum or minimum performance, just think while you're driving. What's the speed limit of 78? 55. And what do you drive? 80. See? Right? Because if speed limit was the maximum, you driving 80 would never happen. Because it would not be possible. So word limit has nothing to do with max and min, okay? Nothing to do with max and min. Word limit is just unfortunately chosen like that way. And we know that it just produces y values. So now we're going to take a look at two more cases real quick and we're done. The first case is exactly the e to the x case. Looks like this. So we are taking a look at the limit of e to the x. So if I go as x approaches 0, I will get answer 1. Why? Because the value is 1. I'm just computing y value for it. Nothing special about it. Here is sine x. Limit as x approaches pi over 2 of sine x is 1. Thank you. Because here's pi over 2 and it's 1. Now I have to, for both of these examples, populate those blue and red arrows. Red approach, red approach, red approach, red approach, and then blue, 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 and blue. To contrast these two examples, I'm going to put the step function. Let's do piecewise, actually it's better. So let's put on this side this, and on this side that. So if you look at this piecewise function, I will say the word clearly, because you know it. We have x for all x is less than 0, and we have x squared minus 1 for all x is bigger or equal than 0. So that's the piecewise function we have. What is the limit as x goes to 0 of this function? Well, looking from the left, it looks like that the left is giving us 0. How about the right one? -1. So what now? Yes? D and E does not exist. Limit doesn't exist because you can't have two values be the limit at the same time. As you approach from the left, you're in Canada, you approach from the right, you're in the US. Well, where are you? It's now someone's going to say North America. Just, So, and maybe I should actually, let me put the red circle and a blue circle so we know that there are two different values. So now I'm going to write that the limit as x approaches 0 minus, which is the left approach, we denote the left approach by putting that little minus there, of f of x is 0, and the blue approach is limit x goes to 0 plus f of x, which is -1. And I'm going to put them together like this and say not the same value, hence does not exist. You will discover this if you do the chart, obviously. From the left, you will be getting 0. From the right, the trend would be -1. 0 and -1, not the same value. There is nothing you can do. So, the theorem. The theorem states, if the left limit, and I'll put in parentheses, limit x approaches a minus, is the same as the right limit, which is limit x goes a plus, then limit x approaches a minus of f of x equals the limit x goes to a plus f of x equals the overall limit. It doesn't fit. X goes to a f of x, which is some number L. So I'm going to just notationally show over here. So guys, this we had as red so far. This was always blue, and this was in black. That was the color coding. Red, blue, black, so far. So if the left limit and the right limit both give you 9, like in the first example, then the overall limit, that has no pluses and minuses here, which is approaches to both sides at the same time, that's 9. In the example here, this one was 0, this one was -1. They were not the same, therefore you can't claim the overall limit to be that value. And believe it or not, we're done. Right? Awesome. All right, so homework. What's for homework? I will see you in a week, which means next Saturday. We'll do much more work, obviously. We'll actually finish chapter 2 next week, next Saturday. We'll be done with chapter 2, and we will vote on the first exam. Be here. The homework, if you have the textbook or if you already purchased the MyMathLab, there is a chapter review for chapter 1. So not individual, because I think they have 5, 6 sections and then they have 100 problems each. I believe review has about 50 problems. Chapter 1 review has about 100 problems. No, 52 problems, I believe they have. Try to do as many as you can, because those are the pre-calculus reviews. You know how they put like 6 problems under the same heading, same directions? So try to do 1 or 2 on each one of those first, and if you have trouble, then do them all, like all 6. So try at least, let's say, 1 or 2 for each one of those different groups. And then if you need more, obviously we'll bring the questions next class. We will discuss it before we start new lecture. The homework for 2.2, 2.1 homework, just don't worry about it, because again, it's actually 3.1. So 2.2 homework is extremely important, and that one you need to do whether it's online or on paper. If it's online, then you're done. If it's on paper, just bring it in next class. Class preps, chapter 2. So chapter 2 class preps, nothing from chapter 1, that's pre-calc review. This is calculus course. So you have, again, forget about 2.1 class prep. So 2.2 to 2.7, so you have those 6 class preps, right? And the homework 2.2 and the chapter review. Now, if you have a different kind of book, it has to have, right, Larson book or any other book will have introductory chapter. So just do homework from that. Again, I'm not grading the homework in terms of looking over your problems. Well, whatever problems you did from whatever book, it's just fine. Yes? I would say half. 2.2. Yes. One page per section, or one sheet, both sides, or one side, whatever. You can put one on one and the other one on the other side, but do not stay for 2 papers that are all 2.1. Yes. Homework 2.2. Either in a book or online, whatever. No, if you're doing from the book, it says which problem you are suggested to do on the syllabus. If you are doing it online, do what's available. You know, try to, for 2.2, try to get them all. For the review, some of you are very good with pre-calc. They'll do 10 problems, and there will be people who will actually do all 52 and then ask me for more. So they have to review. Any other questions? Yes. Let's bring everything together next class. Chapter 1 is not calculus, it's pre-calc, so no class prep for chapter 1.
Okay, thank you.
Which part? Roderack or MathLab? Roderack one? Well, you just show up to the meeting. We actually have a Facebook group, we have, but the easiest thing is to talk to me, because this week they will tell me when they meet, which classroom, which everything, so I'll have information. Right now, I don't have that because they never told me. Student government takes a week. There's also a club recruitment day. I think it's happening this week on Thursday, I believe. So you can also go out and there will be a Roderack table. You can sign up, leave your information. But since you're gonna see me, you can always give me information. I'll give it to Manny and Jessica, and they will add you to the list. You guys, just go join the Facebook group. You can find RVCC Roderack on Facebook. Request to join the group because it's closed group. It's only for members. they will allow you to join in, and then you will see activities, events, and all that.
Thank you.
Just talk to members.
All right, see you later, Heather. Thank you.
You're welcome.
I'm not getting RoadRack emails anymore, so I didn't know about the past events.
Yeah. So that's yeah. We're gonna do everything on a Facebook. If you don't have a Facebook account, create whatever.
What is it on Facebook? RBCC
Just
RoadRack?
Google RBCC Roadmap, you'll find it.
Okay.
Alright?
Thanks.
So like meetings, sometimes the hard thing is
We, as I said, meetings. No one cares about meetings. We do events. Events are the ones.
basically we just show up to the events and we could be
Yep.
part of it.
Showing up of the events is the only thing that actually counts. Towards the service award, party time and events are not. Okay, that's it. Thanks so much.